Welcome back to the AW109SP Normal Procedures Podcast. If you've been with us since the beginning, you've walked around the aircraft, you've powered up the systems, you've started both engines, and you've verified that everything is working exactly as it should. That's a lot of ground covered, and we haven't even left the ground yet. Today, that changes. In this episode, we take the AW109SP from the ramp to the air and back again. We'll work through the before takeoff checks, talk through two different ways to get airborne, the hover takeoff and the rolling takeoff, cover what you're monitoring once you're flying, and then bring it home with the approach, the landing, and a proper shutdown. By the end of this episode, you'll have a complete picture of one normal flight cycle in the AW109SP, from the last check before liftoff to the moment the battery goes off and the rotor stops. Let's go. Before you ever pull pitch on the AW109SP, there's a structured set of checks that confirm the aircraft is truly ready for flight. Not ready in theory, ready right now, in the conditions you're about to fly in. The first thing you're doing in the before takeoff checks is managing your lighting. Cockpit lights go to whatever you need for the conditions, day or night. You want to be able to read your instruments without straining. Position lights and the anti-collision light are confirmed on, and left is required for the departure. Landing lights are set as needed depending on visibility and your departure path. Now, pitot heat. This one deserves a pause. The pitot system is your airspeed source. It feeds your IAS, your altitude, and everything that depends on dynamic pressure. If the pitot tube ices over, you lose accurate airspeed indication. You lose altitude data. In certain configurations, you can lose autopilot modes. That's a cascade failure from a very small component. The rule on the AW109SP is straightforward. Turn both pitot heaters on for any flight in visible moisture or rain, regardless of ambient temperature. Not just when it's cold. Not just when you're in cloud. If there's moisture in the air that you can see, whether that's drizzle, rain, or visible mist, pitot heat goes on. This matters because ice can form even in above freezing temperatures if the pitot tube is cold-soaked from a previous flight or from sitting on a cold ramp. Next, the NR switch. You're confirming it's in auto and that your N2 and NR have stabilized at 102%. At this point in the sequence, both engines should be running, and rotor speed should be solid. If you're seeing fluctuations in NR at this stage, that's a signal to stop and investigate before you add any more variables. Now a decision point, the torque limiter. This is an optional feature that some crews enable before every flight, others only use in specific conditions. When you press the TQ limb push button on the collective grip and it engages, the ECU actively prevents you from exceeding the combined AEO torque limit of 220% or the OEI torque limit of 162%. You'll see a limiter on advisory on your displays when it's active. The important thing to understand is what happens if you don't enable it. Without the torque limiter, the ECU still governs the engines, but it does not prevent you from exceeding torque limits. The protection is yours, not the aircraft's. With the limiter on, the aircraft has your back in a high workload moment. Parking brake comes off. When you release it, confirm the Park BRK on caution message disappears from your displays. If it stays on, the brake is still engaged, and attempting to take off with the parking brake set is something you want to avoid entirely. Warning and caution messages, confirm none. This is your last opportunity before flight to see any system issues that have appeared since the engine start checks. The cockpit should be clean. If it's not, understand why before you lift. Finally, if your departure conditions or operator procedures require an engine power assurance check, this is where you perform it. The power assurance check verifies that both engines are capable of delivering the rated power for the conditions you're about to fly in. It's particularly important in hot and high conditions where density altitude affects engine performance. The AW109SP can be taxied on the ground on its wheeled retractable landing gear. It's not as common as on fixed-wing aircraft, but the capability is there, and it's worth understanding how to use it properly. The first step when transitioning to a taxi is releasing the nose wheel lock. When the nose wheel is locked, the aircraft can only move forward in a straight line. You cannot steer directionally on the ground. Unlocking it gives you the ability to use differential braking and pedal inputs to steer. To begin moving, you gently increase collective, just enough to get the aircraft rolling, and apply a small forward cyclic input. The idea is to keep the aircraft light on its gear, not to lift it, but to reduce the weight on the wheels enough that it rolls easily. As soon as you're moving, check your pedal brakes. This sounds like a small thing, but it's a critical confirmation. On a helicopter that you may have just started for the first time in the day, verifying that the brakes actually work while you're moving slowly on a clear taxiway is much better than discovering a brake problem when you're approaching a turn or trying to stop before a runway hold point. Steering on the ground combines pedal inputs for direction and pedal brakes for slowing and stopping. To stop, lower the collective and apply the pedal brakes smoothly. Keep your movements gentle. Aggressive inputs on the ground can induce oscillations in a wheeled helicopter that are uncomfortable and potentially damaging to the landing gear. There are two standard takeoff techniques in the AW109SP, the hover takeoff and the rolling takeoff. Each has its place, and understanding when and how to use each one is part of operating the aircraft correctly. The hover takeoff starts with alignment. The nose wheel goes forward and gets locked. When the nose wheel is locked, you have a predictable, stable platform to lift from. The aircraft will not wander laterally during the lift to hover. Flight controls go in as necessary to bring the aircraft to a 3-foot AGL hover. 3 feet, not 10, not 1. This is the standard hover height that gives you enough ground clearance to check the aircraft, enough proximity to the ground to confirm your controls are responding correctly, and enough height for a safe continuation or a controlled return if something isn't right. Once you're in the hover, you check flight instruments and confirm engine and transmission parameters are within limits. You're also checking hydraulic system parameters. This is not a perfunctory glance. This is a real confirmation that the aircraft is performing correctly in the flight environment. You have weight on nothing but rotor thrust now, and everything needs to be normal. N2 and NR are confirmed at 102%. In the hover, this is your expected rotor speed. The NR schedule is 102% below 75 knots indicated airspeed. When everything is green, you transition to the climb. The technique here is deliberate. Rotate approximately 10 degrees nose down from your hover datum to begin accelerating, and slightly increase torque to prevent altitude loss during the acceleration. The aircraft needs a nose-low attitude to build speed, and the reduction in lift angle during that transition means you need to compensate with power. As you pass through 30 knots indicated airspeed, you increase torque by 15% and adjust the cyclic to bring the attitude back to 0 degrees. You then continue accelerating to VI, the best rate of climb speed, and increase torque as required for your desired flight path. Once you're above 200 feet radio altitude, the landing gear comes up. The lever goes to up, and you'll see the main util CHRG caution appear briefly during the retraction. This is normal. It's just the hydraulic system working to raise the gear. That message clears when the gear locks. Your confirmation that the gear is up and locked is 3 green lights showing, and the red light extinguished. After gear retraction, NR stabilizes at 100%. This is the normal cruise rotor speed above 75 knots. The rotor speed schedule steps down automatically, 102% in the hover and approach phase, 100% in cruise. If you see NR staying at 102% after gear retraction and acceleration, that's worth understanding. A rolling takeoff is used when a vertical departure isn't practical or efficient, typically on longer, prepared surfaces, or when performance margins favor a ground roll. The setup is the same as the hover takeoff, nose wheel forward and locked. From there, you apply collective and cyclic together to build forward speed on the ground and then lift the aircraft into flight. As you become airborne, you accelerate to VI and rotate to the desired climb attitude. The gear procedure is identical. Above 200 feet radio altitude, the lever goes up, you watch for the main util CHRG caution to appear and clear, and you confirm 3 greens and no red. NR again stabilizes at 100% in the cruise configuration. The rolling takeoff is simpler in terms of aircraft handling. There's no prolonged low hover, no transition through translational lift in the same deliberate way, but it requires more forward space and a surface that can support the ground roll. Know your runway or taxiway before you commit to this technique. The in-flight checklist for the AW109SP is not a one-time action, it's an ongoing confirmation that the aircraft is performing as expected in the cruise environment. The load share switch is set as required for your flight. Load share manages how power is distributed between the two engines. Understanding your operator's normal policy on load share is important. Some operations run one engine harder in certain conditions for fuel efficiency. Others maintain a strict equal share policy. The torque limiter is set as required, meaning you make the same decision here as you did before takeoff. If you engaged it before departure, verify it's still showing as active. Pedals are applied as necessary to maintain direction. Helicopters in forward flight require ongoing pedal input to counteract torque. This is particularly true when power settings change. Be deliberate about trimming the aircraft so you're not holding a constant pedal force for an extended period. Flight instruments are checked for correct indication. Engine parameters are confirmed within limits N1, N2, TOT, and torque. Transmission parameters are confirmed. Hydraulic system parameters are confirmed. These confirmations happen at the start of every cruise segment, not just once at the beginning of the flight. Landing lights, if you used them for departure, are turned off once you're clear of the local area. The landing LT on advisory clears when they're off. Pitot heat, again, check is required for the current conditions. If you launched in clear conditions and you're now approaching cloud or precipitation, pitot heat needs to be on. Compasses are confirmed synchronized. With the glass cockpit in the AW109SP, you have multiple attitude and heading references. Confirm they're all agreeing with each other. Disagreement between heading sources is something to investigate, not ignore. Radios and navigation systems are set as required for the flight. Nothing remarkable there, but don't let the routine nature of it make you casual about it. A radio set to the wrong frequency in an uncontrolled area is a silent failure that doesn't announce itself until you need to transmit or receive and nobody hears you. The approach and landing sequence on the AW109SP begins before you're anywhere near the ground. The checklist starts in the approach phase, and the first item tells you the landing gear is coming down. The gear lever goes to down. You'll see the main util CHRG caution appear during the extension, exactly as you saw it during retraction, and it clears when the gear locks down. Your confirmation is 3 green lights, red light extinguished. If you don't see 3 greens, you have a gear problem, and the procedure for that is in the abnormals. Below 75 knots indicated airspeed, NR stabilizes at 102%. This happens automatically as the aircraft decelerates through the schedule change speed. Confirm it's happening, don't assume. Nose wheel lock goes on. You're preparing to land, and having the nose wheel locked means you'll track straight through the touchdown and any subsequent ground roll or taxi movement. Parking brake is set to off, unless you're landing on a slope. If you're doing a slope landing, the parking brake needs to be on. The reason is straightforward. On a slope, the tendency of the aircraft is to roll downhill the moment the weight comes on. A slope landing with the parking brake off invites uncontrolled movement on the ground. Landing lights are set as required for the conditions and the landing site. For a vertical landing, the standard technique for helicopter operations, you're managing a continuous deceleration from cruise down to a hover, then a controlled descent to the surface. The profile is, reduce airspeed gradually, and by the time you reach 70 feet above ground level, you're flaring and applying collective to pass through 30 knots at 30 feet. You then bring the helicopter to a hover at 3 feet, and descend vertically to the surface. The sequence, 70 feet, 30 knots, 30 feet, 3 feet hover, then touchdown, is a structured approach to what can otherwise become a rushed, unstable arrival. Each waypoint gives you a checkpoint. If you're not at 30 knots by 30 feet, you have a problem to solve before the ground arrives. After ground contact, the collective comes down to minimum pitch or as needed if you're going to taxi. Pedal brakes are applied as necessary. Nose wheel lock comes off if you're going to taxi. The running landing is used when the terrain, performance considerations, or other factors favor a ground roll arrival rather than a hover. You reduce airspeed gradually and apply collective to bring the helicopter to touchdown with minimum vertical speed and a forward speed appropriate for the landing surface. After contact, the collective comes down as necessary to keep the helicopter stable on the ground. Pedal brakes slow you to a taxi speed. Nose wheel lock comes off when you're ready to steer. The running landing requires more forward space and a surface that won't create problems during the rollout. Like the rolling takeoff, it's a technique with a specific application, not the default in confined or unprepared areas. Shutdown is where crews sometimes let their guard down. The flight is over, the destination is reached, and the temptation is to rush through the last steps. The AW109SP shutdown sequence exists precisely to prevent that tendency from causing damage to the engines or the aircraft. Nose wheel lock goes on. Parking brake goes on. Collective is confirmed fully down. Cyclic and pedals are centered and trimmed. The aircraft is in a neutral, stable configuration on the ground before you do anything with the engines. Now the engines come down, but carefully. The mode switches go to idle first, then to off. The reason for the idle step is thermal management. The AW109SP turbines run at very high temperatures during flight. Going directly from flight power to off without an idle cooldown period can leave hot spots in the turbine section that, over time, cause thermal fatigue and damage. The idle step allows a cooldown period before the fuel flow stops. There are two important cautions at this point. First, if you notice any abnormal increase in TOT after shutdown, perform a dry motoring run. An abnormal TOT rise after shutdown suggests residual combustion or hot section issues that need to be cleared. Second, do not apply collective during rotor deceleration. As the rotor slows after shutdown, applying collective loads the mast and can cause droop-stop contact, which is exactly the kind of repeated stress that shortens rotor head life. Below 85% NR, also avoid any cyclic movement except what's needed to prevent droop-stop contact. Once the engines are off, fuel pumps go off, fuel valves close, and the crossfeed valve is confirmed in auto. You're now isolating the fuel system as the rotor decelerates. The rotor brake is applied below 40% NR. Not before. Applying the rotor brake at high NR puts enormous stress on the brake components and can cause premature wear or failure. Wait until NR has decelerated naturally to below 40%, then bring the brake in. The electrical shutdown sequence follows: pitot heat off, miscellaneous switches off, avionics master as required, inverters off, external and cockpit lights off. Once the rotor has fully stopped and you're ready to shut down completely, the rotor brake lever comes forward to disengage. The battery in both generators go off, but only when N1 is at 0%. Never shut off the battery and generators while the engines are still spooling down. You need electrical power available until the engines have fully stopped, both for monitoring and for certain protection functions in the ECU. Post-flight checks on the AW109SP are brief but important. They're the bridge between one flight and the next. If conditions warrant, and in many operations, they always do, pitot static tube covers, engine intake covers, and exhaust covers go on. There's a timing note here that crews sometimes get wrong. Pitot tube covers must go on at least 5 minutes after pitot heat is switched off. The element in the pitot tube needs to cool down before you cover it, or you trap heat that can damage the assembly. Engine exhaust duct covers go on at least 30 minutes after shutdown. The turbine section stays hot long after the engines stop, and trapping that heat inside the nacelle is not good for any of the materials or seals in the hot section. Will chocks go in as required by your operating environment? On a slope, on a surface with any gradient, or in conditions with any possibility of the aircraft rolling, chocks are mandatory. No discussion of AW109SP normal operations is complete without a few minutes on how the aircraft actually handles in flight. Understanding the performance characteristics helps you make better decisions in the air. Handling is conventional in normal forward, sideward, and rearward flight maneuvers. Flight control forces can be adjusted by changing the friction settings on the controls, useful if you have a particular preference or if a crew member has different force preferences for their hand flying style. The torque limiter, when engaged, provides active protection against exceeding combined AEO torque of 220% or OEI torque of 162%. What the limiter does not protect against is N1 or TOT exceedances. Those are always limited at 103% and 970 degrees Celsius respectively, regardless of torque limiter status. Knowing this distinction matters. The limiter is a power protection device, not a complete engine protection system. Best rate of climb speed (IV) is 80 knots indicated airspeed up to 10,000 feet. Above 10,000 feet, VI decreases by 2 knots for every 1,000 feet of altitude. By the time you're at 20,000 feet, VI has reduced to 60 knots indicated airspeed. This reduction makes physical sense. At higher altitudes, the air is less dense, the rotor is working harder to generate lift, and the optimal balance between airspeed and vertical velocity shifts. Flying at sea level VI at high altitude isn't just inefficient, you're leaving climb performance on the table. Auto-rotation in the AW109SP follows the same fundamental principles as any turbine helicopter, but with specific numbers you need to know. Maintain speed within power-off limits. Reduce collective to enter and sustain auto-rotation. Adjust collective throughout the descent to keep NR within the appropriate range. Too much collective will decay the rotor, too little will overspeed it. Attitude controls airspeed, and airspeed controls your energy options. Maximum range, the most ground covered horizontally, is achieved at approximately 120 knots, and minimum NR, minimum rate of descent, the most time in the air, is at VI, and minimum NR, maximum rate of descent, if you ever need it, is at VIN power off and maximum NR. The recovery from auto-rotation to powered flight is a deliberate sequence. Increase collective pitch until the freewheels join, you'll feel this as a change in collective response, and then increase power to arrest the rate of descent. Low-speed steep approaches up to 20 knots and vertical descent maneuvers should be performed with a rate of descent not exceeding 900 feet per minute. This limit is not arbitrary. It reflects the minimum rotor energy margins available during a high rate of descent at low airspeed. Exceeding 900 feet per minute in this regime reduces your ability to arrest the descent without a very aggressive collective pull, which may not be achievable within the power available. That's the complete flight cycle for the AW109SP, from the final checks before liftoff through shutdown and post-flight. Let's anchor the most important concepts. The before takeoff checks are your last opportunity to catch anything that's developed since engine start. Give them the same attention as the pre-flight, don't let the proximity to departure make you rush them. Pitot heat is a condition-based decision. Visible moisture means pitot heat on, regardless of temperature. Don't wait for the airspeed to behave strangely to make that call. The hover takeoff technique has built-in checkpoints, 3-foot hover, system confirmation, then the transition. Each checkpoint is a decision gate, continue or return to the ground. Shutdown is not the end of your discipline. The idle step before off is thermal protection for the engines. The rotor brake waits until NR is below 40%. The battery and generators stay on until N1 is at 0. And the covers go on, but with the timing rules respected. Pitot covers after the element cools. Exhaust covers after 30 minutes. Getting the sequence wrong doesn't mean disaster, but it's the kind of carelessness that accumulates into maintenance problems over time. You now have the full AW109SP normal procedures picture, from the walk-around in Episode 1, through the engine start in Episode 2, to the complete flight cycle here in Episode 3. Thank you for flying with us. We'll see you in the next episode.